Hello friends, in this video we will see size optimization for differential pair as per bias current. So what we are going to do, first I will explain here. So what we are going to do is we will take a diff pair and we have say some tail current, this is some bias current, I bias. Now Now what we will do, we will vary width of this device. So this is at say VBG or VCM 1.25, and we will plot GM for this devices, GM for this devices with respect to width. We are varying width, and this is GM here, and so this plot will be something like this. Okay, so here I bias equals to constant. So here I would like to explain you this thing, that suppose if you are taking width this one, and then you are getting GM this. Okay, so this is your requirement, say this is some value, say GM equals to GM1. For your gain or bandwidth you need some GM. So for this width and the bias current you have decided, say I bias, for that if you calculate, your width is this one, and this GM one is the requirement. According to that you are getting say width W1 for device. So here if you see that this is not optimized size or optimized width for this diff pair, because here this is, you are not taking basically full benefit of I bias. Here even small variation in width, say due to process variation or any variation, your GM will vary a lot. So this is your GM variation according to process or whatever it is. Now if you want to take full benefit of I bias, and if you want your delta GM is smallest, then you should take width, actual width somewhere here, say W2. So that here the variation in width, even in variation in width you don't have variation, this delta GM due to width variation is very less. So it is good idea to size your device width in this region where GM is constant, which is not changing with increase of width, or this slope is very less. So it is not good idea to take width in this region where GM is varying with width. So for I bias, for constant I bias, you should take width in this region where GM is not varying. You should not take in this area. So I would like to do simulation for this, and this technique is known as diff pair sizing or size optimization, diff pair size optimization. So in this way we should decide size of our diff pair for given bias current. So let's do simulation for this. So let's do simulation. So here what I'm doing OP simulation, .op simulation, and here differential input is 0. We are taking common mode voltage only, that is 1.25, you can consider it as a reference voltage or uh, common mode voltage. So here I am taking multiplier MULT, I am putting parameter here, and with step parameter MULT 1 to 40 I am varying with step of 2. Okay, one can also take step of 1. I am taking step 1 and I will run this now. Here bias current is constant, so here bias current is constant, and yeah, so let's run. Okay, so here I have calculated GM square root of uh, GM equals to square root of 2 nu n COX W by L ID in this way. Okay, so here I have calculated through formula, because in cadence we can take direct GM of device, we can extract, but here I need to write this formula. So how to write this formula? Basically, go to plot setting and go to add trace. So in this region you should write this formula. So here all traces are there, so you should write formula here. Now we will see. Okay, so x-axis is width multiplier. So if you are taking, say, multiplier here, say 8, so 8 into width by length, you are getting this sum GM. So till 13 14 it is varying. After that you can see slope is reducing. After this slope is reducing, so you should take your width of device, say more than, multiplier should be more than, or width should be more than 14 into whatever width you are taking. So this is the basically area in which you should buy. So because here GM is constant, so I think if we even books, it is for device, if I is constant, this is, say, W or W by L, and this is GM, so it will come something like this. So this is basically a technique or way to optimize size of differential pair, or you can say it is to size, how to size differential pair with respect to constant bias current. Yeah, thank you.